Imagine the ultimate abyss, a point of no return in the fabric of spacetime, a gravitational monster so powerful that not even light, the fastest thing in the universe, can escape its grasp. This is a black hole. For decades, our understanding, born from Einstein's theory of general relativity, painted a simple, terrifying picture. Anything that crosses its boundary, the event horizon, is lost forever. Crushed into an infinitely dense singularity, its every trace is wiped from the cosmic ledger. Your atoms, your memories, the unique arrangement of particles that constitutes you, all gone. Utterly and irrevocably erased. This seems intuitive, a natural consequence of such an extreme object. But this simple, terrifying picture happens to violate one of the most sacred, non-negotiable laws in all of physics. It presents a paradox so profound it has threatened to break our understanding of reality itself. Welcome to the black hole information paradox. To understand why this is such a crisis, we first need to clarify what physicists mean by information. It's not just the data on your phone or the words in a book. In quantum mechanics, information is the complete fundamental description of a physical system. It's the precise state of every single particle, its location, its velocity, its spin, its quantum properties. Think of it as the universe's ultimate blueprint. The principle of conservation of information, a cornerstone of quantum theory, states that this blueprint can never, ever be truly destroyed. It can be changed, rearranged, or scrambled, but it can never be completely lost. Let's use an analogy. If you burn a book, you might think the information within it is destroyed. The words are gone, the pages are ash. But a physicist would tell you the information is merely transformed. In theory, if you could capture every single particle of smoke, every bit of ash, every photon of light and heat released, you could reverse the process and reconstruct the original book. The information is still out there, just scrambled into a far more complex and disordered state. This principle, known as quantum unitarity, is essential. It guarantees that if we know the present state of the universe, we can, in principle, calculate its entire future and reconstruct its entire past. It's the ultimate law of cause and effect. And this is where black holes become the ultimate cosmic criminals. According to Einstein's general relativity, a black hole is shockingly simple. It's described by only three properties: its mass, its electric charge, and its angular momentum, or spin. This is famously known as the no-hair theorem, the idea that black holes have no other distinguishing features, or hair. So, what happens when you throw something complex, like a book, into it? The black hole's mass and spin might change slightly, but all the intricate information that made the book a book, the specific arrangement of ink molecules, the sequence of letters, the story it told, seems to vanish. It's not just scrambled like the burnt ashes, it's gone. The black hole's exterior tells us nothing about what fell inside. It's a perfect cosmic data wipe. This created a monumental clash of titans in the world of physics. On one side, you have general relativity, the theory of the very large, which describes gravity and the smooth, curving nature of spacetime. On the other, you have quantum mechanics, the theory of the very small, which governs the bizarre world of particles and probabilities. For most of the universe, these two theories operate in their own domains. But at the event horizon of a black hole, they collide head-on, and they give us completely contradictory answers. Relativity says the information is destroyed. Quantum mechanics says it absolutely cannot be. You can't have both. This paradox was thrown into sharp relief in the 1970s by none other than Stephen Hawking. He made a startling discovery. Black holes are not entirely black. Due to quantum effects near the event horizon, they should leak a faint glow of radiation, now called Hawking radiation. Over immense timescales, this radiation causes the black hole to lose mass and eventually completely evaporate, disappearing in a final puff of energy. This made the problem infinitely worse. If the black hole itself eventually vanishes, then where does the information go? Hawking's initial calculations suggested the radiation was purely thermal and random, meaning it contained none of the original information. His shocking conclusion was that information was truly, physically destroyed. When he announced this, it sent shockwaves through the theoretical physics community. It was a declaration of war on the established principles of quantum science. If information could be lost, it meant our universe was not fundamentally predictable. It meant that at a deep level, the connection between past, present, and future could be severed. It would be like a movie where frames could spontaneously go missing, making the story incoherent. This wasn't just an academic puzzle. It was a challenge to the very logic of the cosmos. The universe, it seemed, had a fundamental bug in its operating system, and it was located at the edge of a black hole. So, we have an immovable object clashing with an unstoppable force. General relativity's black hole, the perfect information shredder, versus quantum mechanics' sacred law of information conservation. For decades, this paradox stood as one of the deepest mysteries in science. If information can't be destroyed, but black holes seem to do exactly that before they evaporate into nothing, how does the universe resolve this cosmic contradiction? The answer, physicists now believe, lies in re-examining the very nature of black holes and spacetime itself, leading to some of the most mind-bending theories ever conceived. The universe, it turns out, has some ingenious tricks up its sleeve to enforce its most fundamental law. The first clue came from the very mechanism that created the paradox, Hawking radiation. Stephen Hawking's initial calculations suggested this radiation was random, like the featureless hiss of static. But what if it wasn't? What if, woven into this faint thermal glow, was the very information that seemed to be lost? The idea is that the escaping particles are not truly independent of what fell in. As a particle falls into the black hole, its information isn't simply erased. Instead, it subtly imprints itself on the black hole's quantum state, and this imprint then influences the outgoing radiation. Imagine dropping a single drop of blue ink into a massive churning swimming pool. At first, the ink drop is gone, but over time, the entire pool becomes infinitesimally bluer. The information of the ink drop is still there, just spread out and diluted across the entire volume of water. Similarly, the information that falls into a black hole might be smeared out and then slowly, painstakingly leaked back out, encoded in the subtle correlations between the seemingly random particles of Hawking radiation. This process would be incredibly complex. Reconstructing the original object, say an encyclopedia, from this radiation would be like trying to reconstruct the encyclopedia from the smoke and ash of its burning, but on a cosmic scale of difficulty. The information isn't lost, it's just unbelievably scrambled. Hawking himself eventually came around to this view, famously conceding a bet he had made decades earlier and declaring that information is in fact preserved. But this raises another question. Where is the information stored before it's radiated away? This leads to an even more radical and revolutionary idea, the holographic principle. Proposed by pioneers like Gerard 't Hooft and Leonard Susskind, this principle suggests that our perception of three-dimensional reality might be a grand illusion. It posits that all the information contained within a volume of space, like the interior of a black hole or even our entire universe, can be fully described by a theory that lives on the boundary of that space, on a lower dimensional surface. It's like a hologram. A flat, two-dimensional piece of film can store all the information needed to project a full three-dimensional image. According to this principle, when you fall into a black hole, you don't simply pass through the event horizon into a 3D oblivion. Instead, the very information that makes you gets imprinted onto the 2D surface of the event horizon itself. Your three-dimensional existence is effectively translated into a two-dimensional scrambled hologram of data at the boundary. From the perspective of an outside observer, your information never truly crosses the line. It stays there, plastered on the surface, a complex mosaic of quantum bits. This surface then acts as the universe's hard drive, holding on to the information and slowly releasing it through the process of Hawking radiation. So, what does this all mean for your hypothetical, terrifying journey? It means that while your physical body would be torn apart by unimaginable tidal forces in a process grimly known as spaghettification, the fundamental quantum blueprint that defines you would not be erased. It would be transformed. It would be encoded on the surface of the black hole and, over trillions upon trillions of years, radiated back out into the cosmos in a scrambled, unrecognizable form. The universe, in its unwavering adherence to its own laws, refuses to let you be deleted. Your information is conserved. You are not erased. You are simply and profoundly rearranged. This resolution to the paradox doesn't just save quantum mechanics, it completely redefines our understanding of space, time, and reality. It suggests that the universe itself might be a grand hologram, and that the ultimate law of the cosmos isn't just about gravity or energy, but about the indestructible nature of information itself.